Good. Okay, sorry for the delay. Some technical problems. Good. So the menu for today is that I will continue the story on non-perturbative RG. In this third lecture of 4, we'll briefly talk about symmetries and word identities. It should maybe only take like 10 minutes. Then the bulk of the lecture will be some hard technical stuff again. Unfortunately, but it has to be done. And then in the last maybe another 10 minutes or so, I'll briefly tell you about background field method, and then Alessia will take over in the fourth lecture, and then apply all these methods so that you can finally see some beta functions, and then also tell you a little bit about the state of the art in the field. But before we start, are there any questions from yesterday? So. No, all good. Okay, then let's get started with some symmetries. So of course, symmetries are a very important concept, as has been emphasized by a lot of people already this week. And we have to discuss a little bit what happens with symmetries when we talk about this Wetterich equation. Because we are introducing a regulator, and if you have a gauge symmetry, you also do gauge fixing. So you might wonder what happens to symmetries when we do these two things. And kind of the story here is that for linear symmetries, the story is very easy because the regulator can usually be chosen to respect the symmetry. Because, remember the regulator is quadratic in the fields. So if the symmetry is linear, you have a good chance that you can pick a regulator that respects the symmetry. However, with gauge symmetries, they're typically nonlinear. Like if you think of non-abelian gauge symmetry or also diff, they are nonlinear, so a strictly quadratic regulator must break them, right? And gravity, it's even worse because, as I told you yesterday, this regulator depends on some kind of Laplacian, and the Laplacian is, of course, covariant, just to respect diff in principle. But if it's a covariant Laplacian, it depends on the metric and the inverse metric. So it's certainly very much nonlinear, which clashes with the idea that it must be quadratic. So certainly there's some extra source of symmetry breaking. We have to discuss that. Okay, so for now, let me maybe first discuss symmetries at the level of just the effective action. And let me also assume that the symmetry that we are discussing is not anomalous, so that the path integral measure actually respects the symmetry. This just simplifies the discussion. If the symmetry is anomalous, then it's not good. Okay, so maybe say a starting point. But symmetry with a linear generator of symmetry, fancy G. So think of something like ON for the moment. Okay, and then I assume that the microscopic action is invariant under this symmetry. Okay, so, and the first question that you might wonder about is what happens to the effective action, right? So starting with the path integral and path integral measure and microscopic action that are all invariant under the symmetry is, you might hope that also the effective action is invariant under the symmetry. That's indeed the case. So let me maybe briefly sketch how this goes. So you act with this linear generator G on a path integral. And what you get is something like this. So once again, I'm talking about a scalar field just for simplicity. So maybe an ON vector. I'm not writing down indices now. So the G simply acts on the exponential. And then simply by linearity, it will pull down the action and the source term. So that will be first term, G acting on the action, microscopic action, and then the source contracted with symmetry acting on the field, and E to the, and so on. So what do we have here? We get, so these are just expectation values, right? So we get that the expectation value of G acting on the microscopic action is basically the expectation value of the source term of the symmetry acting on the field. So here we just use linearity of the linear generator. So kind of by definition, this is good. Okay, so this equation must be true, and for any source. Now let us maybe evaluate this source at this equation at the supremode source that we use to define the effective action. What happens then? So let's say J is J sub. Then we still have that 0 is, well, still the expectation value of the transformation of the action, of the microscopic action. And then we have the expectation value of the supremode source and G acting on phi. And now we simply use the definition. Basically, what is this J sub? Remember the quantum equations of motion. J sub is just the first variation of the effective action. So let me write that down. J sub. So here we get a d gamma d phi, g phi, J sub. And now, so by construction, this object is already at the level of an expectation value, so I can pull it out of the expectation value. The symmetry generator is the linear generator, so I can also pull it out. So this whole thing just gives me an expectation value of the field. So what do we get? We get minus GS J sub plus d gamma d phi G phi. And now what is this? Well, this is just G acting on gamma, right? So we indeed get that the symmetry transformation of the effective action is related to the expectation value of the symmetry transformation of the microscopic action evaluated at the supremode source. So whenever the microscopic action is invariant under symmetry, the effective action is invariant under symmetry. So far, so good. So this applies to linear symmetries. So all very good. Now we briefly have to discuss gauge symmetries, and we have to discuss the regulator. And here I only write down the results. There's a little bit more of an explanation in the lecture notes. So basically, we will get a slight change here, which leads us to what's called the Ward-Takahashi identity. So let's first just discuss still the effective action with a gauge symmetry. For gauge symmetry, you have to introduce gauge fixing in the ghost. And basically, translating this and adding gauge fixing in ghost, we get that, now, let me call it maybe W hat, because I use W for the Schwinger function, I just noticed. So this Ward-Takahashi identity is basically something similar. It tells you about the symmetry transformation of the effective action. And then by doing a similar calculation in a gauge theory, you see that you basically get what you might expect, that the transformation of the effective action is related to the transformation of the gauge fixing in the ghost. And here I assume that the microscopic action is already invariant under this gauge symmetry. What does this equation tell you? Well, for example, in Yang-Mills theory, it tells you that, well, you can break the gauge symmetry, but only in very specific ways, right? So if you dig deeper for Yang-Mills theory, it tells you that you cannot write down a gluon mass. So no gluon mass, for example. So something like you cannot write down m squared a mu a mu a. This is just forbidden by this equation. But there are other breaking terms, of course, because gauge fixing and ghost action do break the symmetry. So there are certain terms that you can write down. A gluon mass is not such a term. Okay, now let's add a regulator. Do the same thing again, and basically you can kind of guess it, what happens. You now have a k-dependent word identity, and it mimics very much the standard word identity. There will be extra term, g that has k, but also an extra term in the expectation value. And this guy also has to be 0. So what's the difference now? So let's talk about Yang-Mills again briefly. The difference now is that I told you that this regulator is kind of a momentum-dependent mass term, and it gaps your modes by a gap of roughly k squared. But this tells you that it actually provides something like a gluon mass, which in the limit k to 0 vanishes so that you get a standard word identity. But it also tells you then, as a consequence, that at finite k, you have to have a gluon mass. Okay, so at finite k, you have a gluon mass kind of brought in by this regulator, because you have to make the trace infrared finite, that in the limit of k to 0 goes away, so that you go back to the standard word identity. So you notice that data as k goes to 0, as k goes to 0, you end up back with the standard word identity. So this is very important. It tells you that if you would make a naive approximation and say, okay, I do not want the gluon mass all along the flow, you're breaking the word identity. You will not get back gauge symmetry for k to 0. This is really, well, it's unfortunate, but this is the game. Okay. This is as much as I have to tell about symmetries. Any questions for that? Yes.
Is it easy to see that equation is connected to gluon mass?
No, it's just an example. So there are a lot of other terms that you can write down, but gluon mass is just a very simple example, which you can see that it's forbidden by this equation. But here, just because of the regulator, if you set momentum to 0, you get a gluon mass term. And to kind of leading order, you get something like a comma k squared is something like the coupling squared times k squared to some kind of leading order approximation. So you see, once again, for k to 0, it vanishes as it must, but at finite k, it must be non-zero. Okay. Good. With this brief digression, we have to discuss the supertrace, right? So yesterday I told you that the supertrace in the easiest case of a flat, so Minkowski, let's say, theory is just a standard loop integral. But now we want to discuss gravity, and gravity means curved spacetime, and curved spacetime does not have a momentum space. So we have to make sense out of this supertrace. And that's the let's start down here. That's the goal for main goal of this lecture, to work out what's going on here. Okay, so for that, let me go by example again. Let's discuss the simplest example that we can think of, that of a free scalar field. Maybe before that, I should mention that if we briefly look at the flow equation again, right? So what should you expect? You should expect, once again, in flat space, the right-hand side should just give you some momentum integral, but in curved space, there should be corrections proportional to curvature. So we would expect that there is something like an expansion in powers of curvatures, and we kind of have to find the coefficients, if you want, of such an expansion. That's kind of the goal that we have in mind. Good. So let's get in some details. So let's start with the following thing. As I said, we just consider a very easy action as actually, let's discuss d dimensions. It's not more complicated. You'll notice once again that I'm in Euclidean signature, so I have a plus sign here, and then just a kinetic term for a scalar field. Okay, so, and basically what I have in mind now is, assume I have such a term in my action, and I want to compute which terms this action generates along the RT flow. That's kind of the idea that's behind now this discussion. That's just the easiest case. And of course, I would have to add also gravity terms and so on to really read off beta functions, but this is not the point now. The point is to understand what the supertrace does. And it's just the easiest way to see that. Okay, so if you now just follow this formula, you will take the second variation of this. The second variation with respect to the scalar field is simply a Laplace operator, right? Which is, if I write it down, minus g mu nu, d mu, d nu. So here you see it's covariant derivatives and the metric. So in general, this is just some curved operator. Okay, so what do we have to evaluate? We have to add a regulator. Well, what would we pick? Well, we have a very simple operator, right? So maybe it just adds some arbitrary function of this operator. So let me pick some function rk that I will not specify now, so that this is deregularized two-point function. What do we have to evaluate with this? We want to evaluate 1/2 the supertrace. Well, the inverse of this, well, if you think now of momentum space, if you could do that, it's something like p squared plus regulator of p squared. Now it's just an operator, right? So we have delta plus rk of delta, inverse, and then k dk rk of delta. Now you see this is just some general function of the Laplace operator. So let me forget about the details. Let me call it, I used too many dummies, sorry about it. Let me maybe use v of delta. Okay, so the goal is now, for the next hour or so, to understand what is the supertrace of some function of this operator. And well, towards the end, I will tell you a little bit about how to generalize this, because scalar field is very simple. If you have vector fields or a graviton, there's some additions here, but it's pretty straightforward. So let's just stay with this simple example. Okay, so I already told you what do we expect. This should be something like closed order momentum space integral. plus curvature correction. So what we expect for this is, so that there should definitely be something covariant that comes out of this. And then, well, there will be a constant term which gives you the beta function of the cosmological constant, which is really just the momentum integral of this, right? So we expect, once again, that this is something like a ddp 2 pi d v of p squared. This is the expectation, that this kind of the flat limit that we should get back. And then there are corrections. The corrections should start with a C1 times R, maybe, and then a C2 times R squared, C3, R mu, and this continues. So generally, we should expect, as I said, something covariant because the starting point is covariant, and then we can expand it maybe in such a formula. Okay, does that sound reasonable? Yeah. Very good. Okay. So how do we get there? The way to get there is kind of once again by a differential equation. And the idea is actually, well, so first of all, maybe doing the supertrace for a general function is very complicated. So let me first solve a simpler problem. Let me first try to understand what is the supertrace of the exponential of some dimensional number times this operator. And the reason for this will become clear later, I hope. But certainly exponential is a nice function. So maybe we can understand this guy first and then try to connect it to the general function. This kind of logic. And I will define this now as, or call this the supertrace of some h of s. And this whole idea will go under the name of heat kernel. I'll just briefly write that down. So heat kernel method. If you want to look for it in the literature. Okay, so we kind of have to specify what this function h of s is. And this h of s, well, we can maybe I'm a bit sloppy here actually. So this will depend on two coordinates, and we have to still kind of take some choice. So these are my matrix elements. The matrix elements basically of this e to the minus s delta, if you think. Now let's maybe simplify what we expect. If you would be in a finite dimensional space, this would be an operator in that finite dimensional space, so a matrix, and then you can write down matrix elements. And that kind of carries over to a continuous spacetime. So let us define the matrix elements. Actually, that's right. Sorry about that. This is the h of s. So let's define the matrix elements. These are now h of x, y, and s as sandwiching this function or this operator h of s between two positions eigenstates, assuming that this thing exists. Good. So these matrix elements, and this is where the name comes from, fulfills the heat equation. Okay. And as I said, once again, differential equation, that's nice to solve. So we can actually make some progress. So this matrix element fulfills the heat equation. We take the s derivative. This is the same as minus delta acting on the x coordinate. And we have the initial condition that h of x, y, 0 should be the delta. Okay, and you can kind of convince yourself, like naively, that if you take this e to the minus s delta, you take an s derivative, it just pulls down a delta. So kind of at an operator level, you can see where this comes from, and this is just at the level of the matrix elements. So this hopefully looks reasonable. Okay. And here, once again, so this subscript x just means that this operator acts only on the x coordinate. And in the following, I will not write down the x anymore. All derivatives, when they act on such a biscalar, so it's a scalar at x and a scalar at y, will only act on the x coordinate, just for simplicity. Good. So we have to solve a heat equation. Who knows how to solve a heat equation? One, very good. And so I assume that you all know how the solution to the heat equation looks like, at least in flat space, right? So in flat space, we know what the fundamental solution is. Fundamental solution is exponential, right? Up to some factors. So there's a 1 over 4 pi s to the d half. And then there's an e to the minus x minus y squared over 4s. Okay, this should look familiar, right? Yeah. Okay, very good. Okay. So if this, so this is just the example, kind of the starting point, and we'll hopefully see in a few minutes that this actually gives you back this momentum integral. So if this, we now can finally at least formally define what the supertrace is. So the supertrace of e to the minus s delta is this, I will explain this remaining trace in a second. Is the measure, and then it is simply the matrix element, so this h x y s at coinciding points. So e x h of x x s. So basically the functional part of the supertrace just means that we take the coincidence limit here, whereas this small trace is any kind of index trace that we still might have. So in the case of the scalar field, we do not have this, it's just the identity. But if you have like a vector field, this just the traces over the indices. Or if you have multiple fields, it still traces over this field space. But for our example, as I said, this is just the identity. Okay, so as I said, this guy here is called the coincidence limit, because we take the limit of coinciding points, and we, for brevity, just write that as an over bar over the function, and then function depends on whatever remains. This just saves some writing. When did we start? At 45. Okay. 42. So we have like 1 hour left, basically. Yeah, perfect. Good. So let's maybe quickly check that this makes sense. That this definition actually reproduces this momentum integral, and then we try to generalize this. So on the one hand, what's the coincidence limit of this guy? I take y going to x, so this gives 0, exponential of 0 is 1. So certainly the coincidence limit of the flat heat kernel is just this 1 over 4 pi s to the d. Okay. Now let's come back to here. to our expectation that the supertrace in flat spacetime should just be a momentum integral. And now we discussed this e to the minus s delta, which is now OV. So what is the integral ddp 2 pi d e to the minus sp squared? Well, how do you do this integral? You go to spherical coordinates, for example, in d dimensions. And well, I hope that you can do this. Of course, you can do this. And you see after a few steps that this is indeed 1 over 4 pi s to the d half. So this matches. So at least to the zeroth order, this indeed makes sense to define a supertrace in this way. Okay. So what's the task now? The task is to try and generalize this to curved space. And while I clean, let me know if there are any questions. Yes.
When I normally look in a book on the e-kernel method, it gives me often the one loop effective section. But you were saying that you're doing it going to be more general than that.
So I would put it the other way around. So if you do one loop like trace log formula, you usually use the heat kernel. But heat kernel is just a way to give you a supertrace of log weight. It basically defines exactly this, the supertrace of e to the minus s of some functional of some second order differential operators. It's really just solving the heat equation in a curved space. Yeah. More questions? Okay. Good. So how do we solve this equation in curved spacetime? Maybe it's a good idea to try and make an ansatz that is based on the flat space heat kernel. Okay, so what is the minimal extension of this that has a chance of solving this equation in curved spacetime? And then maybe you can actually solve for whatever we introduced. So let's make an ansatz. So for sure, I want to keep anything of this prefactor. This is just this 1 over 4 pi s to the d half, because it does not really depend on coordinates or whatever. And then I probably want to keep this exponential, but so x minus y is problematic, right? So in a curved spacetime, this is not really a geometric quantity, but what do we have in a curved spacetime? A geodesic distance, right? So maybe let's use that one. So I will now use this sigma. I will tell you in a second what exactly it is. But this will not be everything, unfortunately. We'll have to multiply another function, omega of x, y, and s. And this is kind of the non-trivial part, the meaty part in this. So but first of all, what is this sigma? So if you compare these two formulas, you see that this is something like 1/2 x minus y squared in flat spacetime. So it's half the square of the geodesic distance in flat spacetime, and it will be the same in curved spacetime. So this is 1/2 geodesic distance squared. Okay. It's sometimes called the word function. Yes?
Are you assuming some features of manifold, like it should be non-singular, smooth everywhere?
Essentially, yeah. I mean, to make sense of this, you kind of have to, right? So I will assume no boundaries. and no singular points.
And he's still in Euclidean.
Yes, so this is all Euclidean. And kind of the reason behind this is probably that if you look at this operator e to the minus s delta, in Euclidean signature, this is bounded, whereas in Lorentzian signature, delta can be arbitrarily negative, and then you might run into trouble. And you probably want to generalize this with a Fourier transform instead of a Laplace type transform. Yeah.
When we are the 1/2 here,
That's just convention, a historic reason, I guess. Yeah, people just use this. I guess if you take the derivative, then you get something like the distance. Maybe I'm not sure, to be honest. It's just convention. Okay, geodesic distance, and of course, if I take the coincidence limit of this guy, so coinciding points, which I told you is just an overbar over sigma. What's that? 0, yes. What's the distance between x and x is 0. Good. But there's another really nice property that we have to use to make some progress. There's a function, or kind of a fundamental equation for this word function. And it tells you that 1/2 d mu sigma d mu sigma. Right, this looks really, it kind of looks like a kinetic term, right? This is just sigma. And this is true, I should make, yeah. This is true for any x and y. Okay, I will not prove it, but you can show that this is true for the geodesic distance. And we make ample use of this. Okay, so I told you what the sigma is. So kind of up until here, we have an understanding of what this heat kernel should be. And this remaining function omega is what we have to solve for. Okay. And if you think a little bit more about it, so maybe if you have a sharp look at the definition again, so we had this e to the minus s delta. This tells you that s has the mass dimension -2, because delta has mass dimension 2. So this suggests somehow that this maybe has an expansion in force of s, which comes with curvatures. Because so certainly for flat spacetime, this is just 1. But let me maybe write that down. So this should be something like 1 plus curvature. But how should this appear? Just by kind of mass dimension. So this is dimensionless. So this should always come in combinations s times r, where r is some general curvature, or square root s d, where this is just a covariant derivative, and then of course all indices have to be compacted. So this tells you that if this makes sense in a flat space limit, this should have some power series in powers of s. At least in asymptotic series, yes.
Am I correct to think the choice of vacuum is irrelevant here?
So in a sense, we kind of, this is an asymptotic expansion that we are going for. So you're kind of somewhat close to flat spacetime. That's kind of the assumption. So you should be in a vacuum that is close to the one that you will have in flat spacetime.
Then somewhere reinforce kind of Hadamard condition.
It's a bit difficult to talk about this because we are in a Euclidean signature, but you would probably be in, probably depends on the differential operator that you're considering. Yeah, I'm not entirely sure, but.
And then you would apply this also to the sitter background, right?
The sitter has is Lorentzian signature. We can talk about spheres, for example. That should work. It does work. Yeah, but for spheres we can use something different. On the sphere, this is a compact space. You know the eigenvalues of the Laplacian. So you can just sum over the eigenvalues, and then it's a bit more straightforward. So we have something like 45 minutes left.
Yep.
Okay, so the main task is now to try and compute this omega. Yeah. How do we get this omega? Well, we have to use our ansatz and plug it into the heat equation and see what happens. Right? So I just write down the final result and throwing out factors of the exponential and this 1/4 by s to the d half because they are unimportant. And what you get is the following. You get a differential equation. Squared. So this, as I said, is just plugging in this ansatz into the heat equation. So what we have is, well, yet another differential equation for some function omega x y s. So we didn't really gain a lot. We just rewrote the equation. But now comes kind of this expectation that we say, okay, let us make a further ansatz and say we are interested in the small curvature limit, so some asymptotic expansion. And then we say, okay, it's maybe reasonable to expect that it comes with powers of s because we want nothing like square root of the curvature or something like that, so it should be regular. And then coefficients a n x y. And this is as s goes to 0. And the boundary condition for this guy is that a 0 coincidence limit is 1. This is just once again the flat limit. Okay. So basically we just use power series ansatz to solve this equation. So plugging that in and then solving order by order in powers of s gives you a recursive relation between different ANs. How does this look like? I'll tell you. This is somewhat lengthy again, unfortunately. What can you do? So you see it's recursive. We have an over here, we have the derivative of an over here, and then the second derivative of an minus 1. And of course we have to impose that a minus 1 is 0. I keep forgetting how long do I have left?
We have 40 minutes.
40 minutes, perfect. Good. Once again, I need some space.
37.
37, okay. Everybody on board? So
We have a question. Actually.
Yeah.
So this part, this is also for any kind of operator, or this part of it is a Laplacian and the background is gravity background.
So for now, all the formulas are for just the Laplacian. You can generalize it. So maybe it's a good point to say how the generalization looks like. So you can generalize here. So the first generalization that you can do is instead of Laplace, you add a constant piece, something like a curvature. So think of maybe, I don't know, R/6 or something like that. That's a typical operator. And then what changes is basically you look at e to the minus s delta plus this R/6, and you play the same game. That's the first thing that you can do. The second thing is you have indices, so you have maybe a vector field or something like that, then your operator is maybe something like this plus mu. And then the only thing that changes is that now you have indices everywhere, right? So basically this omega now is a bivector. I think it should be mu. And what do I mean by bivector? It has an index mu at x and it has index nu at y. So it transforms as a vector at x and it transforms as a vector at y. Same thing for gravity. Then you have 4 indices here in your operator, and then you have a bi-tensor. And then if you have a gauge covariant derivative, there's also basically a linear term hidden kind of in the Laplacian, but the same thing goes through. One thing that also comes here with once you have indices is that you get some additional terms because you have that the commutator on your basic field, let's say this would be a V rho, is not 0. So because of this, you will get additional terms in this expansion here for this AN, just because derivatives don't commute on basically also this AN. So also this AN is a bi-tensor, so it's a tensor at x and at y. And if you have commutators for a scalar field, you don't get anything, but for vectors, tensors, and so on, you get something there.
And then could you have in that operator something like d mu d nu? So not too fast and
it's more complicated. So I think you can, but you have to work really hard. So this method works best if you have what's it called? So basically the leading order of your differential operator is just a Laplacian, yeah. So, but in principle you can generalize it. It's just a lot more work. Yeah. Any more questions? Okay. Good. So of course I cannot solve this equation exactly again, so I have to do some order by order. So let's maybe try to get the first non-trivial coefficient, right? So what we're just to recap, what we're interested in the end is the coincidence limit of this guy. So the coincidence limits of these AN. I already told you the boundary condition is that A0 bar is 1. So the first non-trivial thing that we can compute is A1 bar. So let's try to get there in maybe 20 minutes. That's ambitious, but let's see if we get there. So, well, what do? We take n equal 1 and take the coincidence limit of this equation. Okay, so n equal 1 and equal incidence limit. What do we get? So n is 1 minus d half plus, now we take the coincidence limit of d squared sigma, coincidence limit of A1 plus coincidence limit d mu sigma, coincidence limit d mu A1 minus coincidence limit d squared A0. Okay. What do we see? So certainly we have this A1. So this is an equation for A1, that's good. But then it gets a bit concerning here. Take the coincidence limit of the derivative of A1. This guy is not the derivative of the coincidence limit. That's important. So that's potentially problematic. And then we need the coincidence limit of d squared A0. And then once again, this is not the same as the d squared of the coincidence limit, which would vanish because A0 is 1. So also this guy is not a 0. Okay, so doesn't look good, right? Maybe to make some progress, let's look if we can get an equation for d squared A0 coincidence limit. How do we get that? We take n equals 0 down there, and we take a d squared on this whole equation, and then take the coincidence limit. And if you do that, you get a pretty lengthy equation, but I still want to write that down because it shows some features. What do we get? We have a 1/2 d squared sigma coincidence limit. A0 coincidence. D mu d squared sigma. D mu A0. And then minus d½ plus 1/2 d squared sigma coincidence limit. D squared A0. D squared d mu sigma. D mu A0 plus d mu sigma d squared d mu A0, and then to d mu sigma d mu A0. Let's inspect this equation again. So, well, over here A0 in coincidence limit is just 1, so that's good. Well, d mu A0, that's not so nice. We may have to derive an equation for actually d mu A0. D squared A0, that's good. That's what we want. D mu A0, once again, not so nice. Well, 3 derivatives of A0, not so good. And then also 2 derivatives of open indices. So somehow this doesn't really look promising, but well, maybe this sigma saves us, right? So you see that all these problematic terms also come with coincidence limits of derivatives of sigma. So maybe if we are lucky, these terms drop out. Okay, so we kind of have to come back to this fundamental equation for this world function sigma. So 1/2 d mu sigma is sigma, which holds outside of the, yeah. Let me check. It was mentioned that we expand around vanishing curvature R. Can you elaborate on this? Doesn't this mean that we essentially do perturbation theory? It's not really perturbation theory. It's this is just, for the moment, this is one way to solve this equation. Okay, you do not have to do this. It's just the simplest way to understand how this equation works. There are generalizations though. Does that answer your question? Yes, okay, thank you. Good. So let's come to this equation. So let's maybe first of all just take the coincidence limit. D mu sigma is sigma. Well, what's the coincidence limit of sigma? This is just 0, right? What does this tell us? Well, remember that we are in Euclidean signature. So, and this is the norm of a vector. And in Euclidean signature, the norm of a vector is 0 if and only if the vector itself is 0. So here we see that the coincidence limit of d mu sigma is 0. Oh, that's really good. let's look at this n equal 1 equation again. This d mu a1 coincidence limit multiplies the d mu sigma. That term is gone. Phew. One term less to worry about. Good. And now what can we do? Kind of same strategy now. We take derivatives of this equation and then take the coincidence limit. So taking one derivative gives you d mu sigma, d alpha d mu sigma is d alpha sigma, which we already know is 0, but also this side is 0, so we don't learn anything. Let's take another derivative, and then once again taking the coincidence limit. I skip some steps now, because it's really straightforward to derive this. So we get, and this looks more promising. So we get, if you look sharply here, that, well, basically the square of something is the thing itself. And the only tensor that satisfies this is the metric. So from this we learn that the coincidence limit of two derivatives of the sigma is just a metric. Nice. Let's look at the equations again. So with this, we first of all learn that over here, this two derivatives on a0 uncontracted actually gets contracted. So very good, we get a d squared a0 over there. And then we have a d squared sigma here, which is just d, right? So if we just contract the indices of this guy, this is just d. What does that mean? That's minus d half plus d half, that gives 0. Okay. Things are getting easier. Very good. Yeah.
Why is only the method satisfying that? I mean, any projector would satisfy that.
You have to argue a little bit more than I'm doing here, but basically it also just follows from the definition of the sigma that it is just the geodesic distance. Yeah, so I'm skipping a little bit the argument here, sorry. Yeah. Okay. Taking another derivative, taking coincidence limit, what do we get? We get d beta, d alpha, d gamma, sigma plus d gamma, d alpha, d beta, sigma is 0. I already inserted some of the results that we derived. Now for this combination, we have to commute covariant derivatives to get it into the same form. If you do that, and I trust that you know how to commute derivatives, that just gives you Riemann tensors, okay? And if you do that, you get the following expression. So 3 derivatives on sigma plus r alpha delta beta gamma d delta sigma is 0, but this guy is 0, so also 3 derivatives of sigma is 0. Okay, does that make sense? So let's consider mass dimensions. So we see that 2 derivatives of sigma is dimensionless. 3 derivatives of sigma have mass dimension 1. So there is some tensor with 3 indices and mass dimension 1 that is local. Not really, so that's kind of expected. Okay, then we still need 4 derivatives of the sigma because we need a d squared sigma, and then just repeating the thing over and over again. What you learn is that d mu, d rho, d sigma is, well, now we have it 2 derivatives, but mass dimension 2, so we could get a curvature, and indeed we get curvature. And it's actually 2 different Riemann tensors. Okay. And as I said, this is very straightforward computation, just repeating the same pattern. It's just a bit too lengthy to now do this. And then we can contract indices, mu with nu, rho with sigma. And what we get for this guy is simply minus 2/3 r. Okay. So actually we can now come back to our A's. What happens? What happens is, so what have you learned? We first have learned that d squared sigma coincidence limit is d. Did I miss the 1/2 here maybe? I missed the 1/2. So this guy is 0, so that's just a factor of 1 in front of the A1. This guy is 0. So we learn that A1 coincidence limit is just d squared A0 coincidence limit. Very easy. It's more complicated if you continue this. What do we learn here? D squared sigma is minus 2/3 r. This guy is 0 because it's free derivatives. It's over there of sigma. Here, d squared sigma is d, so this guy goes. This guy goes. This guy goes. And then what do we have here? d nu sigma is g mu nu, so this guy is 2 d squared a0. So basically, almost everything vanishes. Great. And we have that 2 times d squared a0 minus 1/2 times 2/3 r is 0. And I hope that I didn't make a mistake, but from this we should learn that, yeah, d squared a0 coincidence limit is r over 6. So we divide by 2 and we get r over 6. Ooh, didn't make a mistake here. And then, okay, A1 is the same thing, so r over 6. So, what do we have? What have we learned? Let's go over here. We have learned that the coincidence limit of this omega is 1 plus s over 6r. Cool. And of course, now you can continue this whole thing. I would not recommend doing this by hand, but using some computer tensor algebra for that. There's this really nice package called Exact for Mathematica that you can use for this to automate this, because it gets really messy really quickly, as you can imagine. Okay. Let me. So, we know, at least in principle, know how to take the trace, the super trace of this exponential of minus s delta. And the last step to get to the super trace that we need is to relate this to a general function.
For being recursively in this way, we are going to adjust the values that consider limits, right?
In the end, we are interested in the coincidence limit because I wiped it away. So the super trace is defined as the coincidence limit of this h.
So I mean, in this context, there's no use of knowing the non-coincident limit, but can be in the way
In some cases, you can compute it. Like if you are on kind of easy spaces, right? Like a sphere. If you know that you're on a sphere and you only want the Hecon on a sphere, you can compute it exactly, or on a torus or something like that. For a general space, I think you cannot, because so let me maybe say this. Here I did not assume anything about the manifold, except that it's kind of well, it doesn't have boundaries and stuff like that. And this gives you an asymptotic expansion. And you see that if you look, for example, on a sphere or hyperbolic space, we compare the two, they have different topologies. And you see that in the large S limit, if you want, have the global properties of this heat kernel differ. which you kind of expect because once the Laplace operator sees the global structure, you must get differences on different spaces. But this asymptotic expansion for small s is universal. Yes, something soon? No. Okay. There is 20 minutes? 20 minutes. Okay. So 10 minutes for getting back to our original supertrace and then 10 minutes on the background field method.
Thank you.
That's okay. I can do it in 22. Okay. So let's take a step back. We wanted to compute this guy. So what's this? What we have is, don't worry about the 1/2. We do have this guy. How do we relate it to? Well, let's make some assumptions again, right? Let's assume as a function, maybe, this v can be written as an integral of a different function v tilde of s e to the minus sx. What is this? This is an inverse Laplace transform, right? So basically the statement is, I want that there exists a function v tilde whose Laplace transform is my original function v. Let me assume that this goes through. Now maybe in the end, we practically don't need it, but let me for now assume that I can do this. Okay, and you see why I want this, because if I now write this v of delta as some integral e to the minus s delta, I'm exactly in the case that we discussed for the heat kernel. Then I have to assume that I can pull in the supertrace into the integral, yada, 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 take the supertrace there, and then I have some expression. Okay. So with this in mind, maybe I can write my supertrace as 1/2 as a space-time integral. As this S integral is inverse Laplace transform of V. And then what do I need? Supertrace of e to the minus s delta, but I just told you, now it's gone. This is just the coincidence limit that we computed. So what do we get? We get this 1/4 pi s to the d12. And then we get this asymptotic expansion that we computed. So flat limit plus s/6r, that's the thing that we computed in the last half an hour or so. Okay. So in principle, you could say, well, that's some expression, right? If I can compute this v tilde, I can maybe do the s integral and then I'm done. But now we don't really compute inverse Laplace transforms because that's once again an integral transform. Solving an integral is really complicated. Can we do something about this? Maybe we can transform this back into an integral of the original function. That would help already, right? Because I don't want this extra step. And there is, well, as you might expect. So let's maybe have a brief look at the structure of this guy, right? So what happens here, I told you that this is an asymptotic series in powers of s, but here we have 1/s to the d12. So the structure of this guy is, there will be some terms with negative powers of s, and then one term with 0 powers of s, and then terms with positive powers of s. So these are the cases that we have to discuss. And there are two nice formulas. Formula 1 for n larger 0, we have the following equation. The integral over s, an inverse Laplace transform of some function, and strictly negative powers of s. So these are the first terms in this expansion. What is this? I can write this as 1 over the gamma function of n. Still an integral, I'll get rid of this. Some power of the variable, and then my original function, v. Very nice. And you can prove that pretty straightforward. You prove it kind of in the opposite direction. You assume that this is correct. You insert your assumption that you can write this as an integral transform. You commute the integrals. You do the z integral because then it's powers of z and the exponential. You know how to do that. And then you see you get exactly the second side. So I leave that to you, or maybe it's also written in lecture notes because we are running a little bit out of time, but you can show that. So this, this deals with the first terms here, but eventually we get 0 and positive powers of s, and there's a different formula for that. So now for n larger equals 0, we have the same integral, but now with positive powers of s. And it's even easier. I get a -1 to the n, and then the nth derivative at argument 0. How do you see that? You kind of see this by writing something like e to the minus sx here and evaluate it at x equals 0. And then powers of s can be gotten by x derivatives of this guy, still everything evaluated at 0. But then you get integral over v tilde of s e to the minus sx, which is your v, still derivatives taken, and then evaluated at 0, and you get this. That's kind of the logic here.
Is that n less than 0?
Larger equal. So this is larger than 0, so you have strictly negative powers. And here it's larger equal 0, so you have 0 or positive powers. And this covers all the cases that you encountered here.
Then you write 2 cases for n greater than.
It's just more convenient to have the minus sign here. Yeah. Because otherwise you get gamma of minus n or something like that, and then might be confusing. Okay. So, final step. So we don't have to compute the inverse Laplace transform. We can just use these 2 nice formulas and write the supertrace of our original function finally in the following way. Yes. Yeah. What if v is log? Which happens when computing the one loop? Yeah. For the logarithm, the question is what happens if v is the logarithm? So v of x is logarithm of x, which happens for the one loop effective action, then v n of 0 diverges. Here you have to be a little bit careful because this integral transform gets an extra term. So the inverse Laplace transform of log doesn't exist. It's divergent. You get a slight modification here, but it still kind of goes through. Yeah. Thank you. Good. So let us finally write down this guy, at least asymptotically. I have this factor of 1/2, which is just in front of the supertrace. I get the 1 over 4 pi to the d12, which is just there. I get a ddx square root g. And then I get a 1 over gamma d12 and an integral 0 to infinity dz z to the d12 minus 1 v of z. Okay. And then I get a plus 1 over 6 r. Right, that's the heat conduct coefficient over there. I get a 1 over gamma d12 minus 1 and another integral now with 1 power less of z. And this continues. So this is how you compute a supertrace in an expansion around flat. Maybe one last comment on this. You see that the dimension d somehow appears only in very specific places. And it turns out that this is a general pattern. So up here in this expansion, if you continue it to higher orders in curvature, there are no factors of the dimension. Which is kind of interesting observation, because in all these recursive formulas, you could expect that at some point there's a factor of d or something, but it does not happen. These are dimension independent. The only position where dimension comes in is this 1 over 4 pi s to the d half. Just an maybe interesting side fact. Good. Any more questions about the heat current? Yeah.
It seems that like the procedure to get there
Mhm.
very similar to using like Riemann normal coordinates.
Yeah, there are different ways to get to the same coefficients. This is just one way that is covariant and relatively straightforward also to implement on a computer, or you can just push it to somewhat high orders.
But still, this is not perturbative.
It's an asymptotic expansion. It's, if you want, perturbative in this S, but yeah, it's an asymptotic series in S. But it doesn't mean that it's perturbative in any coupling or something, right? This is just making sense of the supertrace of some differential operator.
And is there in general hope to like some part of this asymptotic expansion or anything else?
Yeah, so as I mentioned, if you know enough about your manifold, you can compute the heat current. For example, a sphere, you know the eigenvalues of the Laplacian on the sphere. So one alternative way to get a supertrace, so let me maybe write it down on the sphere, you know what the eigenvalues of the Laplacian are, and you know the multiplicities. And then on such a space, supertrace of some f of delta is simply the sum over eigenvalues with multiplicity m lambda n of f lambda n. That's one alternative way to, right? So that only works if you know a lot about your manifold. And this heat current method just works generally. It's just agnostic about the space.
Still perturbative around flat.
This expansion, yes, but as I said, you can do the kind of opposite limit, but then you expect to see topological stuff. So you would have to put some boundary conditions, basically.
But there are also some like partial resumations which are more general, like the covariant expansion and the
Yeah,
last time expansion.
Yeah, so what you can do is, so instead of, basically this is actually a derivative expansion that I showed here, you can do partial resummations of this type where you kind of get a whole function of delta. Yeah, that is possible, even on a general space. So that would be a curvature expansion. Yeah, but thanks for the comment. Yeah. Okay. You want to? No. Okay, so I have 12 minutes left, I guess. Yeah, very good. That's basically how much I need. So once again, let's take a step back. What have we done? Or what have I told you? We've started to discuss non-perturbative renormalization with the goal to investigate gravity. And I derived for you this non-perturbative renormalization group equation. And now I hope that I made sense out of the ingredients that go in there. So mostly the supertrace that we did today, but also I talked about the regulator yesterday. And now what is left is to actually apply this equation to gravity. And in these last 10 minutes or so, I will get this discussion started, and then Alessia takes over in the next lecture, and then also tells you about some recent results and maybe some open problems. Okay, so gravity. Now the thing with gravity is, again, well, we have a symmetry, diffeomorphism symmetry, right? So let me maybe write that down. So the symmetry is kind of stored in the Lie derivative of the metric. This is V nu plus D nu V nu. And this is, of course, a nonlinear symmetry because it has the covariant derivative, which also includes the metric. Okay, so let's discuss gravity with the FRG. And as I've told you yesterday, to make any progress with this Wetterich equation, you have to make an approximation. And the approximation that I will show you, or that we show you actually, that I start now, is simply to say, let's start with GR and see how far we get. Okay, so what happens is we take the GR action, we promote all the couplings, in this case too, to k-dependent couplings. So lambda k and gk. And the first sanity check of this whole scenario, is to compute the two beta functions connected to these two couplings and see what happens. If there is a fixed point, critical exponents, and so on. Because kind of the hope is that you don't have to go too crazy with the approximation to see whether this works or not. Okay, so and now, well, gravity, as I said, is this stiff symmetry, and we have to introduce a gauge fixing, we have to introduce a regulator. Luckily, Luca told you already a little bit about it. What we have to use in the end is what is called the background field method. So what we do is we take the full metric and we split it into some arbitrary background metric plus a fluctuation. And I should stress 2 points here. The first point is we are working with an arbitrary background. Okay, we do not have to assume that this is flat. And just for conventions now, I will not introduce a factor of this kappa, so it's square root g basically into this expansion. That's just how we usually work here. Okay. This is not the only way how you can do things. I should maybe briefly mention that this is what we will use. You can also do something like this. So you take the exponential of g bar inverse h to parameterize your metric fluctuations. And this has some advantages that are discussed at length in the literature, because here, basically, this is a one-to-one correspondence between metrics and background metrics plus fluctuations, which is not the case here. You see that for certain choices of h, for example, if it's minus g bar, you get into trouble because it's not a metric anymore. So here you kind of have to restrict the path integral in principle, whereas here for Euclidean signature, you simply integrate over any h, and you're guaranteed that you still get a standard metric that you integrate over in the original coordinates.
So just to make sure I understand, h is not assumed to be small in any way.
No, it's really anything. It's just a way to introduce some background structure and then symmetries attached to the background structure. Okay, so we will use this just for simplicity. From now on, all the indices are raised and lowered with the background metric, as is done, as has been done by Luca as well. And of course, since our background is general, there will also be background curvature and background covariant derivatives.
Right, is
Yeah.
it totally general or does it have to be solved by same equations?
It's general.
Yeah.
Yeah, it's general, it's off-shell. Yeah. Okay. And then the last thing that I will briefly discuss is how bad this really is. Okay, so kind of in connection with our gauge symmetry, what happens if we do this? And you can kind of convince yourself that now your standard diffeomorphism transformation kind of can be implemented in two different ways. The first is quantum diffeo. That would be G bar transform that does not transform, and all the transformation goes into the H. That's certainly one way of implementing diffeo. And there's a second one, which is called the background diffeo, which kind of puts the transformations where they belong in a sense. So G bar transforms as G bar plus the Liouville derivative of G bar, and H transforms as H plus the Liouville derivative of H. Okay. And now we have to discuss what happens if we introduce gauge fixing and a regulator. What happens is that background diffeos are preserved. They are not broken, whereas quantum diffeos are broken. So in a sense, the physical diffeomorphism symmetry is kind of carried by the quantum diffeo transformation. And of course, now you can play the same game that we played at the beginning of this lecture. There are mode identities related to the breaking of quantum diffeo, and they are connected to the regulator. The last thing that I want to mention is not only does the standard diffeo split into two different implementations, we get a new symmetry, right? So if we make some arbitrary transformation of G bar goes to G bar plus X, and we transform H to H minus X, the full metric does not change. So somehow we are really shooting ourselves in the foot with doing this, but it's unfortunately the only way we can do RG with gravity, at least that we know of in the continuum. So let me write it here. So we have G bar goes to G bar plus X, and H goes to H minus X. This is a new symmetry, at least for this linear parameterization, which we call split symmetry. And once again, there's a symmetry identity related to it. I will not write it down now, it's a bit technical, but basically I can sketch it. It's called a Nielsen identity. It basically tells you what the difference of derivatives is of the effective action with respect to the background metric and the fluctuating field. There's an explicit expression for this, which is on collection notes. So of course, what do you expect here? You expect the gauge fixing, the ghost, and the regulator. So very complicated stuff that you kind of have to deal with, and it's actually one of the open problems to properly deal with this. But this is just how it is, and I think now it's time for some refreshments, if there are no more questions.